To summarize, if we have the determinant of our 2 by 2 submatrices to be equal to -1 as part of the design process, then the baseband impulse responses for analysis and synthesis, they are identical with this sign. So h of n is equal minus g of n. If we also would like to have orthogonality or para-unitarity, we need symmetric baseband impulse response, and we have h of n is equal to minus g of n, and h of n is equal to h of the 2 times capital N minus 1 minus n. And these are two important properties which we obtain for our baseband impulse responses. A simple example for this case, where the determinant is equal to -1 and orthogonality, is the sine window. And the sine window is given here. This case also leads to para-unitary polyphase matrices because it is a symmetric window, symmetric around its center. The sine window is often used in the MDCT filter bank because it's easy to design. We know it leads to perfect reconstruction and still has a reasonable frequency response. For instance, the raised cosine window would even have a better frequency response, but it would not lead to perfect reconstruction if it's also used for the synthesis. So it does not fulfill the condition that the determinant should be equal to -1. For perfect reconstruction, we need to compute a different synthesis prototype. So para-unitarity is good for an easy design for perfect reconstruction. So remark that for para-unitary polyphase matrices, Parseval's theorem for the energy conservation still holds, so in the limit of long sequences, meaning that the total energy in the signal in the time domain is equal to the total energy in all subbands. This can be used, for example, for the estimation of the energy of the quantization error in the reconstructed signal, or the total energy of quantization error in the subbands is equal to the energy of the quantization error in the reconstructed signal. This is important, for instance, for design quantizers. Observe that we don't necessarily need the symmetry of our baseband impulse response. If we only have the determinant condition that the determinant is equal to -1, we still have h of n is equal to minus g of n, but they don't need to be symmetric. In this case, Parseval's theorem does not need to hold, but it can still hold approximately. Observe the factor of c to the power of -1, which we obtained in the inversion of the delay matrix d of z to obtain causal filters. This means we get a delay of one block, and it is the source of the algorithm or the system delay and of our analysis and synthesis filter bank, if the synthesis follows directly after the analysis filter bank. In general, the system delay is the blocking delay of n-1 samples to assemble the signal into blocks of length n, plus the delay needed to make our matrices causal. This is a very important result. It's telling us that the system delay is equal to the blocking delay of n-1 samples. It's necessary to assemble the signal into blocks of length n, plus the delay needed to make our matrices causal. In the case of the MDCT, we get a block delay of n-1 plus the delay from our delay matrix, which results in a total delay of 2 times capital N minus 1 samples. In the MDCT case, our filter length is L equals to 2 times N, hence our total or our system delay can also be written as ND equals to L, the filter length, minus 1. We see that the delay is coupled to the filter length. This is true in general for orthogonal or para-unitary filter banks, and also for longer filters we obtain ND is equal to L minus 1. This is one of the drawbacks of orthogonal filter banks. To obtain lower delay, we need to take non-orthogonal or non-para-unitary matrices. So non-para-unitary matrices or filter banks can have some important advantages, but they are more difficult to design.